Today, our journey through this wonderful world of maintenance will stop at reliability station. I will introduce you with some basic concepts and give you a brief introduction of reliability discipline. Let us start our journey looking at introduction, history, and concepts. I will start with a small story. Many years ago, I was traveling in India in a very small town. I visited an electronic shop buying some batteries for my torch. Then comes a lady and asks for a user. And when the salesman showed her many varieties, many models, then she asked one very good question. Ask which one is the best, which one will last longer, and what are the guarantees that it will do the job. What she was focusing, even though she looked like an uneducated old woman, what question she had on her brain is reliability of the user. So that was the main question. She didn't define reliability. She has never been to any lectures on reliability, but the basic thing comes to her mind is reliability of the product. Let's look at another case. A defense minister going for a shopping of fighter aircrafts or military hardwares. The fundamental question they ask, mission reliability. Will it be able to perform the tasks? So, a old lady from a small village shopping for less than $100, or a defense minister going shopping for more than billions of dollars, reliability becomes the fundamental point for decision making. So this reliability is very important. Let's look at the history. History of reliability. What happens? Prior to World War II, it was mainly intuitives. You know what is intuitive knowledge? Knowledge built without any scientific foundations or basis, but you know about it. That's intuitions. It is subjective. People said this much reliability is good, that is not good. And of course, it was qualitative. No measurements of reliability in numbers or any foundation, scientific foundation. But what happened after World War II? In fact, if you look into the history, even before the World War II, some of the railway company in the US, they started working on statistical calculation, knowing the failures of reliability. But after World War II, most of the military equipment became very complex, and it was very difficult to maintain them. They were failing without any indications. So discipline of reliability starts evolving. And in 50s, it became a sound foundation for making decision about the purchasing of equipment, developing new equipments. So people started using the concept of reliability in planning for purchasing, planning of design. Reliability become a ground, or rather main foundation for designing reliable systems. Reliability calculations started people calculating using the models, probabilistic models, etc. And of course, the main core of this lecture is operation and maintenance. Rather, our focus is on maintenance, or anything that is unreliable will bring maintenance into the picture. So in operation and maintenance point of view, reliability is very important basic concepts one should know. So every maintenance engineer should be aware about the reliability of fleet they are maintaining, or reliability of the operations they are going to perform, so that they can take precautionary actions or preventive actions. Looking into the areas, so as I said, reliability, when it started developing from military, it started with the aviation industry. You know, generally there's a lot more emphasis on reliability of flying planes than a cycle, bicycle. If you're using a bicycle, we don't talk about reliability. But when you go into shopping for a aircraft, reliability is very important, as I said earlier. So focus was brought to reliability, and aviation industry was the driver for development in reliability discipline, and they were the leaders. And of course, since military has a lot of money, resources, they were the leaders in that. Then it migrated to nuclear power industry. Their safety is of great concern, because you can't afford to have failure in a nuclear power plants. And to ensure failure-free operations, they start working on quantitative methods for reliability in planning and operation of nuclear power plants. And gradually, the concept of reliability was adopted by many industries, process industries, chemical industries, mining industry, many all other industries. So gradually it started from aviation, it migrated to nuclear and process and other industries. So today, if you go to any industry, people are aware about the maintenance engineers are aware about reliability concepts. They are using it in their day-to-day planning. So if you summarize, so reliability has become an integral part of design, operation and maintenance for most of the engineering assets and systems. So that's the brief account of the history of reliability engineering. Now, how can we define reliability? We have to look basic definition of reliability. It's defined as ability of an item to perform a required function under given conditions for a given time interval. So there are 4 important things here. Ability of an item, that's a probability. To perform a required function, you have to define the function, what the component, item or equipment has to deliver. And under given conditions, that's also important, for a given interval of time. So the definition consists of 3 main basic parts. One is ability of item, often expressed in terms of probability of success, that is failure free, as we'll be looking into more detail when I come to the sections on failures, etc. A specified time of operation. So reliability and time of operation is closely related to each other. Means shorter period of time, it will be more reliable. That we know from our practical, our day-to-day applications and use. Anything that is new is more reliable because we have not used longer period of time. So a specified time of operation and a specified operating condition. What is very reliable in a very nicely room temperature may not be reliable in a cold climate, may not be reliable in a dusty conditions. And typical example are automotive industries. When they develop a car or a buses, they are very reliable on a good road, but when they are tested on a bad road, they don't work. So operating conditions are very important item while discussing reliability or in design of equipment, system, etc. Now, when you want to measure, we have been talking how to measure common man. Commonly, reliability is expressed in terms of mean time to failure when it is a non-repairable items, or mean time between failures for a repairable items. So these 2 terms will be coming across when I'll be discussing more how to calculate reliability, how to assess reliability, how to predict reliability of the items. Let's look into some of the basic concepts that we'll be using in our discussion in next few sections and next chapters. One is reliability theory. What is reliability theory? Reliability theory consists of that provides the foundation for our all estimations, calculations. It consists of like a statistical work, statistical models, etc. How do you develop them? That's a theory. Reliability science, that deals mostly with the properties of materials, how you understand the degradations of an item so that you can estimate reliability properly. So causes of deterioration or part components of failure are studied under headings of reliability science. And then of course, reliability technology we'll be using sometime. These are the tools, reliability tools to understand reliability science, science part of the reliability, and develop new understanding so that reliability theory can be further developed. So tools, methodology forms part of reliability technology. But one more thing you should remember, many times science facilitates development of technology and technology helps science to develop further because technology gives you an opportunity to understand things in a better way. So science and technology are very closely related to each other. We have to remember this. Next concepts you will see many places is reliability engineering. What is reliability engineering? It deals with the design, constructions, use of knowledge from science, use of knowledge from technology, keeping the economics of entire process into pictures. Like you optimize things here. You look into the life cycle cost, etc. That's a reliability engineering. And it also often provides link between science and technology. Last but not the least is very important item is management, reliability management. If you are managing a product development, the management process ensures that things are done within the budgets, are produced as per the customer requirements, manufacturing is performed in right way, it is delivered in a right way so that customer gets the right reliability at their application point. So reliability management takes care of design, allocating resources, manufacturing, like parts are produced as per a specification, and operation systems are maintained properly. That forms a part of reliability management. So if you look, each items are important and management connects to each of these concepts. Now we'll look into some of the reliability notions. And as you see, many times I use the word design. Design, you think about reliability. So design reliability is one very important concept. When you design an item or an object, you calculate how much reliability it should have, and that forms the basis for developing design reliability for whole machines or systems. Then inherent reliability. When you design something on your drawing board, you send it for manufacturing. There may be some margins, like there'll be some play, and parts cannot be produced as per the specification, so you compromise little bit on reliability, and it can be little lower than the can be. You may get some of the components may be what they were designed, but inherent reliability, the parts produced from manufacturing, that reflects inherent reliability characteristics. And third one is a operational reliability. When you take the components, item or machine in applications, maybe as a designer I thought the level of dust in a particular area will be this parts per million, but it is more than that. Maybe we need to maintain the machines in a different way, and that will impact the reliability of the components. Because you remember I said in an operating condition must be specified. If there is a variation in operating condition, it may change. It may change for good, it may change for the bad. So if conditions are worse than you visualize or you thought, you planned during design, then it may be bad. It will get a lower reliability, I mean to say. As with time, reliability become very popular. Now different reliability discipline has evolved. Let's look, we have been discussing about hardware reliability. I defined whatever definitions I gave, it was for the hardware reliability. Two more areas have established themselves in their own rights. One is software reliability, and it has developed as a discipline in its own right. And there are many literature, many people are studying it separately. Why? As you will understand, everyone is using software in every actions. Morning when you get up, you look into your mobile phone. That's based on software. Or you want to switch on your light, that is also controlled by some form of softwares. So our life has become much more dependent on softwares. If softwares are not functioning, we'll not have electricity, we'll not have water, we'll have a lot of problems. You'll not be able to make your coffee in the morning. So discipline of software started becoming one of the most critical area for studying societal risks, etc. Discipline started evolving since late 70s, but last 15-20 years it has become very important. How do we define software reliability? Its a definition is more or less like hardware. It is defined as the probability that a software will perform its function failure-free for a specified period of time under given operating condition. So remember, software is also having operating conditions. Let's have electrical system, and if I draw more currents, maybe particular software controlling the supply may not work properly. So operating conditions are very, very important. Also operating time. The programmer can put some restriction on the time, and your software, your computer will not function. It will stop automatically after using for so many hours or so many minutes. So these are the things we studied during the software reliability, and it's how it will perform the task it is assigned to perform it. But even more important, we are living in an age of automation. We're talking about autonomous vehicle. We are talking about self-flying planes, drones, etc. Everything is controlled by softwares. But there is a person behind it who designed it. So if he fails to visualize the conditions, if he fails to understand the functional requirement, there will be a problem in the autonomous system, automatic systems. Because who programs the softwares? It is the humans. And we are trying to take these humans from the work more and more. And the remaining person becomes very, very important, very critical. If he does one mistake, the whole system will collapse. So human reliability has become very important during the last 15-20 years. Even though discipline started being evolving in 50s, and the equipment started becoming complex, people start talking about human reliability. And you look at the one figure here. The sailor has failed to, he misjudged the wind directions, wind velocity, etc. and it has come on the ground. So this is one example. Many times you'll read, if you're reading the newspapers, etc., you'll see a plane crash. And I can guarantee you 50% of time the reason is human failure, human error. That's a measurement of human reliability, etc. So this is one of the discipline that is evolving very much with autonomous driving. People want to go for autonomous driving to remove the humans, but the remaining person becomes very important because one person is controlling the software, controlling the connectivity, communication, etc. So this discipline will develop even further, and it is going to be central in many system design, etc. And it's defined exactly like the softwares. It is a probability that a person will correctly perform a required function. If I'm going to land, I'm a pilot, I should follow the procedure and land the plane in defined way during a given time period without any error under given working condition. One more example I'll say, I'm very efficient and effective worker in a room temperature at 20 degrees Celsius or so. But if I'm asked to work in a minus 30 degree, I may not be that effective and efficient. And I'm more prone to do mistakes and error, leading to issues of human reliability. So operating conditions are equally important in all the three areas. Given period of time is equally important in all the three areas. So these disciplines are evolving. I will be trying to explain these concepts with help of some functions and some of the nicely colorful diagrams. Let's look at here. This function describes the machine reliability. Common sense says with time reliability decreases, and that's very common. But if you see here, in the beginning, reliability starts at lower level because there are some teething problems, problem of failed components being assembled, people working in a failed assembly, etc. So in the beginning, there is a problem, and especially in case of big assets, it takes a month, sometimes it takes 3 months to start a system that will perform as expected. So such problem will come in the beginning. This is a very important thing. And after some trial run and all, things stabilize and you get the expected reliability and performance. This is the machine. What happens in case of software? Software has more or less the same problem. It will work, and suddenly whenever new program is released by Microsoft or by any big companies, they have the same problem. There are a lot of bugs, and when bugs are improved, immediately it gets a very sharp rise in reliability. And as time goes, people remove the bugs, software programs becomes more and more reliable, and it will stabilize at certain points, or it gets upgraded. But what happens to human reliability? See, as a child, we are less reliable. And people say at the age of 16 to 18, you start becoming more responsible. We hear this word from our parents. Now he is responsible. Now you're 18 years, you are responsible. They mean that we are becoming more reliable. That's one of the reasons that when you apply for driving license, you are not allowed to drive cars in many countries if you are less than 18 and 16 years of age, because you are not reliable. And see that time you become, it's a constant reliability. You become more reliable, maybe more matured, but a point comes your reliability starts going down. Usually in good old days, people used to say if you're 60, your reliability goes down. But I'm going to be 60s. I'm little bit. I think I'm more reliable and it will go up to 80 years. I should start thinking about it. So now in a modern time, people say old 80s, time 80s, now modern 60s it will be like we are very fit like a 40 years old. We are more reliable. I never feel any problem driving cars, anything. So this point has moved to 80 years. For 30, 40 years ago, it was used to be on 60 years old. So that's a good part. Maybe I'm still hoping that in 10 years it will move into the 90 years. You never know. And then reliability goes down. You can see that in people with old age, etc. They are never assigned responsible duties because they are not reliable. But that's the fact of life, is it not? I have been talking about reliability is very important. It gives us ensures the functions. We give our services. We get everything thanks to reliability. So I'm going to give you some summary of the economic impact. In operation and maintenance, because this lecture is more concerned with maintenance, technology, management, etc. So if I could calculate quantitatively reliability of machine systems, I can very easily calculate the optimal maintenance interval. I should know the cost and reliability, so I can decide about when to take the system out for maintenance. Lot of money is lost, lot of resources are lost because people take too early for maintenance or too late for maintenance. Both are undesirable conditions. Optimal replacement decisions. If you have a fairly good understanding of reliability of your component systems, you can make decision when to replace your asset. If I have a car, reliability is the only criteria I'm using. I'll be able to replace my car at the right time, not too early, not too late, because I lose money in both cases. In a big companies, bus transport companies, you run 200 buses, then you will be able to calculate a standby fleet sizing, because standbys are important because some buses are not working. I can rely on the standby buses, etc. So standby calculation are used for exact fleet sizing. How many buses we should have? If I need when I was working in the mines, we used to have we must have 16 big trucks to produce the planned production volume. But we calculated using reliability that we should have 21 trucks because our availability, reliability was different, not as much expected. So we bought 5. But similar production in other mine, our competitor had a 23 because their maintenance was not so designed. So reliability was the common denominator to calculate the number of standby we needed. I'll be demonstrating this in next lecture, how to calculate the standby and how reliability influences our calculations and purchasing of extra machines, etc. And of course, reliability provides the basis for optimum operating time before a machine can be taken for maintenance. If you don't follow that, you will have unplanned stoppages leading to indirect cost. That is undesirable. Let's look the cost of reliability. We have been talking. Reliability is not free. I say reliability is good. If I have good reliable machines, I don't need maintenance. But you remember, reliability is not free. As I want more reliability, I should be ready to pay more. But we should optimize it because good reliability reduces the cost of maintenance and repair. So we should find a point where I can get the optimal value, and that optimal value here is reflected by this yellow line. And if I'm doing some optimization, so this is the optimum reliability for a given part of components or items. This is the point we should try to design in the system. So this is one very simple example, but in reality it's a bit complex. And some of the examples we'll be taking in the next lectures. You will be able to see some of these things. Now, summarizing this short introduction, history and basic concepts. We have looked into the basic concepts of reliability, such as reliability theory, reliability science, engineering, technology, management, etc., which are forming the foundation of reliability discipline. We also look how cost and also impact of reliability, and say they are overlapping each other because cost and impact, they are related to each other. If I put more higher reliability, I need more, it becomes more costly, but it will have a positive impacts on the asset lifecycle cost, etc. Thank you.